Every Linux program lives in user space, which means it cannot touch the disk, the network, or memory on its own. It must ask the kernel through system calls, openat for files, connect for sockets, map for memory. Syscalls are the only real conversation a program has with the operating system, so observing them shows exactly what your code is doing. Strace is a detective that sits between your program and the kernel. It uses trace with trace_syscall to attach to the process, and the kernel politely stops execution at every syscall entry and exit, whispering the arguments and return values to strace before letting the program continue. Your program never knows it is being watched. 5 flags cover 90% of real strace usage. F follows fork children, so you trace the whole process tree. E trace equals openat, write, network, file filters to only the syscalls you care about. C prints a summary table of counts and timings. O writes everything to a file instead of the terminal. And PPID attaches strace to a process that is already running, no restart required. Strace shines in 4 classic debugging situations. When a file open fails with enuint or eches, strace shows the exact path the binary tried, and the erno the kernel returned. When you need to know which config file a mysterious binary reads, strace lists every openat call at startup. When a program hangs on launch, strace reveals whether it is stuck waiting on a syscall or still spinning. And when performance is off, C summarizes which syscalls dominate runtime, so you can profile hot spots. Strace is the first diagnostic you reach for when something behaves strangely on Linux. Before you launch GDB, before you rebuild with debug symbols, before you guess, run strace and watch the syscall stream. The kernel tells the truth, and strace lets you hear it. Welcome to this walkthrough of strace, a diagnostic utility that intercepts and records the system calls a process makes as it runs. Before we begin, we clear the terminal to start with a clean workspace, giving ourselves a blank canvas to work from. First, we verify that strace is installed on the system. The which command searches the directories in your path, and returns the full location of the executable, /usr/bin/strace in this case. If it returned nothing, you'd need to install strace through your distribution's package manager. Now we run our first real trace. Strace attached to ls/tmp, filtered to only show openat syscalls, piped through head to limit the output to the first 5 lines. Each line shows the syscall name, arguments in parentheses, and the return value. Openat returns a file descriptor number that the kernel assigned to the open directory. Next, we generate summary statistics with the C flag, which counts how many times each syscall was invoked and measures time and error rates. This is incredibly useful when you want to know at a glance what kind of work a program is doing. For ls running on /tmp, you'll typically see lots of openat and read calls, with most of the time spent in the brk memory allocation syscall. Now let's trace a simple command, echo demo, to see exactly what even the smallest program does under the hood. Here we're not filtering anything, so strace reports every syscall the shell spawns to run echo. Exec launches the binary, brk allocates memory, then write actually outputs the text demo to the file descriptor. It's a great way to demystify what just running a command really means at the kernel level. Finally, we check strace version with the v flag, which prints the program's version string and build information, including which trace scoping mode it was compiled with. This is useful when troubleshooting behavior differences across distributions, or when reporting bugs upstream. Raw strace output is overwhelming, but filtering flags cut it down to size. Use etrace equals network to grab socket and connect calls. etrace equals file for open and read, and etrace equals IPC for pipes and shared memory, or combine all 3 in one comma list. Add eread equals 32 to captured bytes, and y to resolve file descriptors into real paths like /etc/password or socket frowny face 12345. You don't always get to start a process fresh. The p flag attaches strace to any running process by PID, no restart, no lost state. It's the standard move for stuck daemons, hung services, and production triage where downtime is not an option. Stack multiple p flags to watch several processes, add f to follow forks, and Control-C detaches cleanly while the target keeps running. Syscall timing separates guesswork from real debugging. T prints wall clock seconds. TT adds microseconds for cross-log correlation, and TTT stamps the full date down to the microsecond. For latency hunting, R is the killer flag. It prints the elapsed microseconds between calls, so a 4 million microsecond gap jumps off the screen and points straight at the slow syscall. Terminal output is disposable evidence. Log files are shareable. O writes the full trace to disk, perfect for sending to a teammate or archiving an incident. Pair it with a pipe into grep for live targeted searches. Isolate every connect, every failed open, every eches without scrolling through thousands of lines. The two approaches together turn a noisy trace into a searchable artifact. Strace is powerful but not free. The trace mechanism slows the trace process. Expect 2x to 100x overhead depending on the workload. Some applications actively detect tracing and refuse to run, calling it anti-debug behavior. And on modern Linux, the Yama trace_scope syscall restricts which processes you can attach to. A non-parent process often cannot trace a non-child unless the admin changes the scope. Plan around these limits before you need them. The real strength is combining flags into one focused command. Strace ptrace equals network, onet.log. /server follows every child process, filters down to network syscalls only, and writes the result straight to a file for later grepping. That single line is your production debugging Swiss Army knife. Minimal noise, full visibility, shareable artifact.